Okay. So in this sort of dead week for labs, we'll have, I thought I'd do sort of a review of principles, introduce maybe a few new things, and what I'm doing in this lecture is trying to go through a specific type of polymer, Kevlar, which maybe you've heard about, and we'll learn about it in detail today. And this will be good sort of, thinking ahead, not for next week's lab, but the week after that when you'll make a, when you'll be working on making a poster presentation or a PowerPoint presentation, we call it, in your lab section. And please talk to your GSIs. Hopefully this next week in lab, you'll be talking to your GSIs about getting prepared for that poster presentation, like picking a viable polymer to work on, and then learning about what a good presentation is like and what the criteria are in the grading rubric for that. So I thought I would, along those lines, I thought I would talk about an interesting polymer that was invented, or discovered rather, I guess both, in the mid-1960s called Kevlar. And it's kind of an interesting story, and I won't go into all the details, but a female chemist was working on making polyamide plastics. For example, nylon is this type of polyamide, but she was doing it with aromatic groups in it, and she found it had unusual properties, and they were about ready to throw it out, but then they decided to go ahead and spin it into a fiber, and they found they made a fiber that was nearly as strong as steel. And that's a remarkable property for plastic, especially when you think about its density. And as you've already been sort of, you sort of had some practice thinking about density already, but we can think of density in units of grams per cm cubed, grams per mil. And then you can also think about strength, or tensile strength. And here we'll measure that in units of pressure, megapascals. Okay. So, like I said, it's a really interesting comparison to make between Kevlar, and I'll show you a structure in a minute. Well, actually, there's a picture of it above. And not just steel, not just steel, but hardened steel. As I said in the Wednesday section, this is steel that, when you heat treat steel, in tools that are used to work metals, you heat treat the steel so it's extremely hard. Or if you're a samurai swordsman, this is the kind of weapon you would like to use. You don't use a plain old soft steel sword, you want to use a hard steel sword. So hardened steel is extremely strong. It has, its tensile strength is like 5,000 megapascals. It turns out that Kevlar is pretty darn close to that, 3,700 megapascal. But you might say, well, that's not quite as good as steel. But here's the big trade-off: that the density of Kevlar is say 1.44 grams per cc, but for steel is about 8 grams per cc in density. So that hardened steel, pretty much one of the toughest materials for your dollar steel now can be replaced with a lightweight material. So you can imagine sort of all kinds of applications. In the old days, when I say old days, I'm talking about like the 100 Years of War. People would wear armor, right, in battle, and they'd wear steel, effectively, right? Everyone's seen those kinds of things. And so, that's not very useful for policemen to walk around with armor on, in the old days, like a steel suit. But today they walk around with Kevlar vests because they're obviously 5 times lighter and give you tremendous protection. So that's one great example. The Kevlar vest, the helmets, used in both the police and military. But also, can be useful for gloves. For example, I don't know if you like seafood, but people that have to deal with seafood or always having to shuck oysters or whatever, you got knives around and you could cut yourself. So this is a great way to protect your hands without wearing chainmail. Although you could wear that too. They make that actually. And the other thing, of course, are cords and ropes. So one of the examples I mentioned, which is really, and these are all the uses. I'm sorry, I'm not writing them down. You can write them down. One of the interesting examples is the Mars landing, NASA operation there, where they bring a spacecraft to the outer orbit, and they release some kind of landing unit, and it has to go through the atmosphere, and they have a chute on it, a parachute, and this thing has these nice these nice Kevlar ropes. They're lightweight, because obviously in a spacecraft you don't have metal ropes or whatever that can withstand those forces of coming into the atmosphere like that. So yeah, it's this real space age material, and although discovered in the 60s, still pretty much cutting edge stuff. And so some other things besides body armor and things, you'll find it on bicycle tires. I always opt for these. I always opt for this kind of material because I get lots of glass and stuff in my tires when I ride my bike, so I say, why not put the stronger thing in there, a lot stronger than regular old rubber. And it's also been a replacement for brake pads in cars, which normally had less eco-friendly material or health-friendly material, asbestos, and then you can replace that with Kevlar in the brake pad. So besides body armor and all the other things I mentioned, of course, it's a great material. And it's rough. A space-filling CPK model is shown here. This is a CPK space fill. Like I said, those are all sort of outer van der Waals sort of spheres, making in a single polymer chain. And if you have an astute eye, you can see that you see some 6-membered rings. Those are benzene rings. And then you see a red sphere and a blue sphere. That is an amide bond. Okay, and we talked about that with peptide bonds, and I've talked a lot about hydrogen bonding properties there, and you'll see how that's going to play a major role. Yes. Oh, you can hear me? Yeah. Oh, sorry. Okay. So how do you make Kevlar? Well, it's made from 2 different monomers. Now, the original Kevlar, I forget the gal's name, she had both types of functional groups on the same monomer, so she just had a single monomer. But to make it commercially viable, then they invented this process. Okay. So this is one monomer, and this is a para-substituted, and people might not understand para. I'll explain that in a minute. Phenylenediamine. And I don't know if people know organic chemistry and the substitutions on an aromatic ring, but I'll do those for you here in schematic. So if I have an aromatic ring and I put substituents across from one another, then we call that para. If I put substituents with one space in between, we call that meta. And there's another type of polyaramide plastic like this Kevlar that's used in firemen's uniforms. It's fireproof and uses a meta-substitution version of these chemistries. And then there's ortho. Anyway, those are the various configurations that you can substitute across the ring, of course. There's no other possibilities in those 3. The rest are symmetric. Okay, so that's one of the monomers. The other monomer is one we've already talked about, terephthalic acid. And remember, this has 2 carboxylic acid functional groups, okay, on it, across also in the para-substitution configuration. So you basically have 2 monomers that are para, and you might imagine, well, we'll talk about this in a minute. Go ahead and ask the question. But how might you expect these to come together? What kind of polymerization mechanism would you expect? Does anybody have any idea? It's not called dehydration exactly. Do you remember its name? Condensation, right? So you're going to do condensation chemistry here to bring these together. And if we were going to use there are various methods to do this. We might create water in the process, but we're not going to exactly do it that way. We're going to show you the commercial method, which uses thionyl chloride to activate the carboxylate for attack by the amine groups in the paraphenylene diamine. But in any case, that's just that's a commercial process. But this would be a condensation. This would be a condensation polymerization. Remember that we've only learned two different types. We learned condensation polymerization and additions polymerization mechanisms. So that's useful for studying purposes. And you just have to decide whether you're going to produce a. All right, yeah. So the polymerization chemistry is going to be something like this. We'll take our two monomers, and I'm just going to draw this out in schematic form really quickly. So there's our two monomers, and we'll join those together, and we'll do this in some polymer notation here. The repeating unit, of course, is a dimer of these. And this is our bond that we're going to form repeatedly here. So hopefully everybody can see that. This bond, and so, the name of this polymer is Kevlar, but that's a trade name, right? That's like a brand name. It's a brand name. This is like Levi's jeans, And, but really, its technical name would be a like I said, aramide. And so the question then will be, well, what's the amide part? Well, that's the bond. Okay, that's an amide bond there. And then, of course, the air denotes, the AR denotes the aromatic rings, okay? So, poly makes sense. So, yeah, it's basically a polymer held together with these nice groups. And the reaction is, again, condensation. But we're going to do it a little bit different way than I showed earlier in the course, which was sort of more like a scholarly exercise. This is a practical way of doing it. And we're going to basically create what's called an acid chloride on the terephthalic acid, okay? And the way you do that is you're going to mix this reagent called thionyl chloride, which is very reactive towards carboxylates, carboxylic acids. And with this, you don't need to do much. You'll end up with the following. And you'll end up with a couple of other byproducts here. So you'll have some byproducts as well. You're going to have HCl plus sulfur dioxide, okay? And so I guess you'd use two equivalents of this because you have two sites. In any case, now you can take the acid chloride activated form of terephthalate, acid chloride form, and this will react rapidly with the amine groups and our paraphenylene diamine. Yeah, these guys are extremely reactive, okay? And I'm not going to go through the chemistry, but remember that these will do it. These electrons here on this nitrogen will attack the backside of that carbonyl, and eventually, you'll be some rearrangements there, and the chloride will be kicked off. And so, by having a mixture of these together, you will then generate your polymer, and produce some more HCl. And there's your amide bonds. Your amide bonds are these similar to esters, but instead we have a nitrogen involved. So, and then you'll have some HCl. So you can see that's the basic chemistry, the sort of commercial process for making Kevlar. Now I think the really interesting question is not so much how you make it, but why is it so strong? And on the first slide I forgot to mention this, that basically the strength of Kevlar this is like a culmination of what we've been learning here, that intermolecular forces between the polymer chains are what gives many of the strength properties that Kevlar has. Its lightweight yet strong properties. Makes it extremely tenacious material. So as you might imagine, based on what I just showed you, I mean if you see this central unit, the new bond that's formed looks like this. And I know you're drawing this probably repeatedly, and it's maybe driving you crazy, but you're going to remember it. That's okay. Sorry, but it's good practice. But remember, we have these dipoles, okay? There's actually a pair of them in an amide bond. And as you may know, these types of dipoles are great for, especially when a proton's involved, for hydrogen bonding, right? So they're excellent for hydrogen bonding. And that's what I have shown here in this, again, a slightly different rendering molecular model of a layer of Kevlar polymer chains interacting with each other in a single monolayer. And if you look very carefully at this picture, what you'll see is that you have all these beautiful, and I'll try to do it in a color that's easier to see, you'll have all these beautiful hydrogen bonds, okay? And so not only are these chains being held together by close, nearly perfect jigsaw van der Waals interactions between those edges of those aromatic rings, but they have these beautiful hydrogen bonds zippering the chains together. And what I was trying to say is that Kevlar is amazingly strong from the sum of many small, weak intermolecular forces between the polymer chains. And unlike the previous lectures, we were talking about cross-linking, and it gives you all these great properties like in stretchy rubber and this and that. There's no cross-links in Kevlar, yet it's as strong as steel. And all that strength is basically given by these a sum of many weak, say 5 kilojoule per mole hydrogen bonds, along with the next new interaction we'll talk about in a minute. But the idea is that in these polymer chains you'll have these So you might, this is really what this diagram above is showing, but in a larger format so that you can actually visualize the hydrogen bonding groups. But you can see the way these things tend to want to rotate up and down in this plane of interaction. So then, the next chain can come in and line up. And it's going to get a huge energetic benefit if it aligns in this particular orientation, because that way it will produce the most hydrogen bonds. And that is how it will gain the lowest free energy, or the lowest energy configuration. And that's the name of the game in chemistry. So, this is kind of redundant exercise, but it gives you, you should be able to do this. And you can see when you do this exercise that everything, if I were really religious about this, I would have made all my bond lengths, perfectly, perfect distances and so forth. And you would have seen that the hydrogen bonding donors and acceptors line up perfectly. And that's because of the regular pattern of this. Also, the other thing that really is conducive for good hydrogen bonding in this polymer is that it's para-substituted. And that makes these polymer chains rigid and long. And then when they orient their groups towards one another, they're in a rigid line. And that makes for a perfect alignment of these hydrogen bonds. You're not fighting the floppiness that you can see in other sort of polymers where the chains want to reorient. So anyway, the bottom line is this, that you get a massive network of hydrogen bonds. And this can effectively make giant sheets, okay? So you can get giant flat sheets that are all held together largely with van der Waals contacts and hydrogen bonds. So you have to think, when you think about a material, you have to now think in 3 dimensions, okay? And so this is one dimension, one set of dimensions in our material, say 2D sheet. Okay, so now the next thing we're going to need to do is build up the sheet into a 3-dimensional polymer, or 3-dimensional assembly of these polymer chains. But to do that, we need to learn a new intermolecular force. You guys are still young Jedis, you don't understand the forces yet, right? So that's the whole point of this course. At the end, you'll be samurais, and I'll give you a lightsaber. All right. You didn't know. So this is a way of drawing an aromatic ring on its side. And you're going to have to forgive me. I'm going to violate all sorts of laws of chemistry here. But it's just it's a thought exercise that before this became a double-bonded aromatic system, which can't exist like this anyway, it had these p orbitals, okay, on each of the carbons that were above and below. They were above and below the plane of the carbon in the ring, okay? And those guys are going to overlap into what are called pi orbitals. Okay. So these are individual p orbitals. And you haven't learned these yet, but I imagine, or maybe learned them in high school. But these guys, this entity right here that I just drew does not exist in reality like that, okay? But I'm trying to convey the sense of bonding occurring in the formation of pi bonds. And what's going to happen here is that they're going to combine and form basically a toroid, okay, like a donut of electron density. You can think of it as a halo. Sweet innocent, and it's hard for me to convey this. Sweet innocent benzene has halos above and below it. These are the pi clouds, okay? That's the Greek letter pi. These are pi clouds that exist above and below, so the ring. Huh? No, P means P. Those are P orbitals, S and P and D orbitals, on up. And then when they start to make bonds, when S orbitals overlap, you get sigma bonds. I I can do that for you. So I'm sorry, I didn't even think. If I had 2 atoms and they're going to make a sigma bond, then they'd have S orbitals. These two, they would sort of it's a little bit more complicated than that, but in any case, if we had something like carbon or something like that, actually the orbitals would hybridize, the S and P orbitals, these sp3 hybridization, and then you get overlap, and you call that overlap of those a sigma bond. But so there, the S in sigma denotes that the S orbitals are used in these sigma bonds, and those are between the atoms. But when we have pi bonds, or when we have p orbitals that overlap with themselves, we get pi clouds above and below the plane of this aromatic ring, and we call those pi clouds. It is a play of the Greek letter off the P in p orbital. In any case, that's what you have. Now you need to think about electrostatically what's going on. And electrostatically, you have some interesting things going on in a benzene ring. You have, of course, these protons all around the edge. Does anybody know which direction the dipole will go on those? Will it go in toward the ring or out toward, will the arrow point out towards the hydrogens? In towards the ring, right? So that you already have this situation on this ring, okay? So each one of these has a dipole moment pointing inward toward the ring. So that means that those guys are all partial positives on the outside. I'm sorry for those that associate red with negative charge. It's okay. Or, yeah, I'm doing red with positive charge today. Now we have our pi orbitals above and below, okay? And these are going to be delta minus, okay? Because they are rich in electrons, okay? And so you're going to have a very, very interesting and unusual, complicated electrostatic surface on a benzene ring. And many people think, benzene is just a boring old hydrophobic molecule. And no, it's not even remotely like what I just said. It's actually a complicated electrostatic surface, and it can engage in a variety of dipolar interactions, and also what we call this configuration with the sandwich here of a positive charged ring in the middle, a belt of positive dipole in the middle, and then 2 negative clouds above and below. We call this a quadrupole. And you can have quadrupole interactions, quadrupole dipole interactions, all kinds of interesting setups. And that means that benzene rings can interact with each other and get stabilizing different stabilizing configurations. For example,